हेलो दोस्तों, आज हम आपको समझाएंगे पी और एन टाइप मटेरियल्स के बारे में।
तो वीडियो शुरू करते हैं। Effects of impurities on P and N type materials. Since silicon in its ultra-pure form is an insulator, it must be transformed into a semiconductor material by adding some impurities to the silicon. This process is known as doping. Arsenic as phosphorus P or some other element with 5 valence electrons in each atom is mixed into the molten silicon. Selective cooling of the molten material causes solidification to occur across a particular crystal direction. Crystal growth is enhanced by placing a small seed crystal at the end, which is cooled first. The seed crystal is lowered into the molten material and is raised slowly, allowing the crystal to grow onto the seed. The crystal pulled and rotated slowly from the melt as it grows into the shape of an ingot. The result is a silicon lattice with flaws. The elements bond, but numerous free electrons are present in the material from the fifth electron that is part of the valence shell of the doping element atoms. These free electrons can now flow under certain conditions. Thus, the silicon becomes semiconductor. When silicon is doped with an element or compound containing 5 electrons in its valence shell, the result is a negatively charged material due to the excess free electrons and the fact that electrons are negatively charged. This is known as an N-type semiconductor material. It is also known as a donor material because doping silicon can also be performed with an element that has only 3 valence electrons, such as boron, gallium, or indium. Valence electron sharing still occurs, and the silicon atoms with interspersed doping element atoms form a lattice molecular structure. However, in this case, there are many valence shells where there are only 7 electrons and not 8. This greatly changes the properties of the material. The absence of the electrons, called holes, encourages electron flow due to the preference to have 8 electrons in all valence shells. Therefore, this type of doped silicon is also semiconductor. It is known as p-type material or is an acceptor since it accepts electrons in the holes under certain conditions. Majority and minority carriers. Both N-type and p-type semiconductors are able to conduct electricity. In the N-type material, current flows primarily like it does in any conductor. The valence electrons move from one valence shell to another as they progress through the material. Due to the surplus of electrons, the electrons are considered the majority current carriers in N-type semiconductors. Any movement of current in N-type material by the filling of holes is considered the minority current carrier. In p-type material, current primarily flows by valence electrons filling holes that exist in the doped lattice. This makes holes the majority carrier in p-type material. Any current flow in p-type material that occurs without holes valence electrons exchanging with other valence electrons is known as the minority carrier. The progression of a hole moving through a number of atoms. Notice that the hole illustrated at the far left of the top depiction of the figure attracts the next valence electron into the vacancy, which then produces another vacancy called a hole in the next position to the right. Once again, this vacancy attracts the next valence electron. This exchange of holes and electrons continues to progress and can be viewed in one of two ways: electron movement or hole movement. For electron movement, illustrated by the top depiction of the electron is shown as moving from the right to the left through a series of holes. In the second depiction in the figure, the motion of the vacated hole can be seen as migration from the left to the right, called hole movement. The valence electron in the structure will progress along a path detailed by the arrows. Holes, however, move along a path opposite that of the electrons. Combining N-type and p-type semiconductor material in certain ways can produce very useful results. The following section will discuss what occurs at the junction of the N-type and p-type material when a voltage is applied. PN junctions in the basic diode. A single type of semiconductor material by itself is not very useful, but applications have been developed when p-type and n-type materials are joined that have revolutionized electrical and electronic devices. The boundary where the p-type material touches the n-type material is called the PN junction. Interesting and useful phenomenon occur at this contact region. Furthermore, when joined, the entire two-element semiconductor device becomes a basic diode. A diode is an electrical device that allows current to flow in one direction through the device but not the other. Because of this, the semiconductor diode is used in electronic circuits to convert alternating current AC into direct current DC. Thus, The PN semiconductor device can act as a rectifier. An explanation of what happens at the PN junction and how it affects the entire PN semiconductor device follows. A glass-encased semiconductor diode. Unbiased PN junction. The electrical characteristics of an unbiased diode, which means that no external voltage is applied. The P side in the illustration is shown to have many holes, while the N side shows many electrons. When the P and N material contact each other, the electrons on the N side tend to diffuse out in all directions. Some of the electrons enter the P region. With so many holes in the P material, the electrons soon drop into a hole. When this occurs, the hole then disappears. A negatively charged ion is created since there is now one more electron than the number of protons in the nucleus of the boron or gallium or indium atom to which the hole belonged. Meanwhile, in the N material near the junction, the valence electrons that departed for the p-type material leave behind a band of positive ions since there are now more positively charged protons in the nucleus of the arsenic or phosphorus, etc. atoms than there are electrons in their shells. Thus, each time an electron crosses the PN junction, it creates a pair of ions. The area outlined by the dashed lines. The circled plus signs and the circled negative signs are the positive and negative ions, respectively. These ions are fixed in the crystal and do not move around like electrons or holes in the conduction band. They constitute the depletion zone where neither excess electrons nor excess holes exist. The ions create an electrostatic field across the junction between the oppositely charged ions. Because holes and electrons must overcome this field to cross the junction, the electrostatic field is usually called a barrier or potential hill. As the diffusion of electrons and holes crosses the junction, the strength of the electrostatic field increases until it becomes strong enough to prevent more electrons or holes from crossing over. At this point, a state of equilibrium exists and there is no further movement across the junction. The PN junction and the entire PN device is said to be unbiased. PN junction. The two semiconductors joined at the PN junction form a diode that can be used in an electrical circuit. When a voltage source, e.g., battery is attached to the diode with the negative terminal connected to the N-type semiconductor material and the positive terminal connected to the P-type material, it is said to have forward bias and electricity can flow in the circuit. The voltage opposes the electrostatic field at the junction and reduces the potential hill. The positive potential of the battery forces holes in the P-type material toward the junction. The negative potential of the battery forces free electrons in the N-type material towards the opposite side of the junction. The depletion zone becomes very narrow and electrons in the N-type material flow across into the P-type material. There, they combine with holes. The electron and holes continuously come together resulting in current flow. These majority carriers in each semiconductor material increase in number as voltage is increased. This increases current flow. When disconnected from the battery, the depletion zone widens, the electrostatic field strength is restored and current flow ceases. Note that the potential hill or barrier is reduced when connected to the battery as explained, but it still exists. A voltage of approximately 0.7 volts is needed to begin the current flow over the potential hill in a silicon semiconductor diode and about 0.3 volts in a germanium semiconductor diode. Thereafter, current flow is linear with the voltage. Caution must be exercised because it is possible to overheat and burn out the semiconductor device at the junction with excessive current flow. Also note that temperature has a significant impact of current flow in semiconductors. PN junction. When the battery connections to the PN semiconductor are reversed, the diode is said to have reverse bias and current will not flow. The most noticeable effect of reverse bias seen in this illustration is the widened depletion zone. Semiconductor diodes. Semiconductor diodes are used often in electronic circuits. As discussed in the previous section, PN junction diodes offer very little resistance to electrical current when forward biased and maximum resistance when the diode is reverse biased. When AC current is applied to a diode, current flows during one cycle of the sine wave but not during the other cycle. The diode, therefore, becomes a rectifier and changes the AC current to a pulsating DC current. When the semiconductor diode is forward biased, electrons flow. When the AC cycles, the diode becomes reverse biased and electrons do not flow. This submodule will go into further detail on diode parameters, symbols, identification and behavior. It will also detail the operation of various types of diodes and show how they are used in power supplies and other common circuits. Diode parameters. Semiconductor diodes have properties that enable them to perform many different electronic functions. To do their jobs, engineers and technicians must be supplied with data on these different types of diodes. The information presented for this purpose is called parameters. These parameters are supplied by manufacturers either in their manuals or on specification sheets, also called data sheets. Because of the scores of manufacturers and numerous diode types, it is not practical to present a specification sheet here and call it typical. Aside from the difference between manufacturers, a single manufacturer may supply specification sheets that differ both in format and content. Despite these differences, certain performance and design information is required as follows. A brief description including the type of diode, the major area of application, and any special features is normally given in the specification sheets. Of particular interest is the specific application for which the diode is suited. The manufacturer will also provide a drawing of the diode, which gives its dimension, weight, and, if appropriate, any identification marks. A static operating table giving spot values of parameters under fixed conditions is often given and sometimes a characteristic curve. The right side of the graph shows the current characteristics of a diode when it is forward biased and the left side of the graph shows the current characteristics of a reverse biased diode. Finally, the specification sheets provide the diode ratings since they are the limiting values of operating conditions outside of which the diode could be damaged. PN junction diodes are generally rated for the following. 1. Maximum average forward current IFAV. This is the maximum average amount of current that the diode is able to conduct in forward bias, which is directly proportional to the amount of voltage applied. However, there is a thermal limitation regarding how much heat the PN junction can withstand before a structural breakdown can occur. Maximum average forward current is usually given at the maximum power dissipation at a specific temperature, typically at 25 degrees Celsius. A resistor may be used in series with the diode to limit the forward current. 2. Maximum peak or surge forward current IFSM. The maximum peak or surge amount of current that the diode is able to conduct in forward bias in the form of either recurring pulses peak or non-recurring pulses surge. Again, this rating is limited by the diode's PN junction's thermal capacity and is usually much higher than the average current rating due to the time it takes to reach maximum junction temperature for a given current. Current should not equal this value for more than a few milliseconds. 3. Maximum forward voltage drop at indicated forward current VFF. The maximum forward voltage drop across the diode at the indicated forward current. 4. Maximum reverse current IR. The very small value of direct current that flows when a semiconductor diode is in reverse bias mode and is below the peak inverse voltage applied. This is known as leakage current and is in the microamperage range. 5. Maximum reverse voltage VR. Also known as the peak inverse voltage PIV is the maximum amount of voltage that the diode can withstand continually in the reverse bias mode without causing a PN junction breakdown. As mentioned, a small amount of current flows through a semiconductor diode when it is reverse biased. However, at a certain voltage, the blockage of current flow in a reverse biased diode breaks down completely. This is known as the avalanche voltage or Zener voltage. It is the voltage at which a normal diode can no longer hold back the reverse current, and as a result, it fails. 6. Reverse recovery time TRR. The time it takes for a diode to turn off after it switches from being forward biased to reverse biased. For rectifier diodes, recovery time may be in tens of microseconds, whereas signal diodes typically recover in only a few nanoseconds. 7. Total power dissipation. The maximum amount of power that the diode can dissipate in the form of heat when it is forward biased conducting due to some internal resistance. To find the power dissipation, multiply the voltage drop across the diode times the current flowing through it. This rating, measured in watts, is limited by the diode's thermal capacity. 8. Maximum operating temperature. The maximum allowable junction temperature before the structure of the diode deteriorates. It is expressed in units of degrees centigrade per watt. All of the above ratings are subject to change with temperature variations. If, for example, The operating temperature is above that stated for the ratings. The ratings must be decreased, or heat sinks may need to be attached to the diode to maintain its operation below the rated junction temperature. Since many of these parameters vary with temperature or some other operating condition, manufacturers typically provide graphs that show the component ratings plotted against other variables, such as temperature, so that the engineer and technician have a better idea of the capabilities of the particular device being used. Thanks for watching this video.
दोस्तों फिर मिलेंगे अगले वीडियो में। कृपया इस चैनल को सब्सक्राइब जरूर करें। नमस्कार दोस्तों।